How's it going, everybody? Josh, amateur radio call sign KI6NAZ. We're back again tackling the technician license question pool. This series of videos will be good through June 30th, 2022. So if you're interested in getting your technician license, the time is always now. I always think you should have your license. It's just an extra good thing that you have in your mental quiver of tools. So we're continuing right along. What we've been doing is working from the hardest sections down to the easiest sections, and this is the second hardest section. This is section 9, which is about antennas and feed lines, my favorite section. So let's get started. Now, why am I going from hardest to easiest? Well, I think that if you focus on the hardest questions and work your way down to the easiest stuff, you're likely, when you're down here, you're already going to know most of it. So by focusing on the questions that most people miss, you're increasing your chances of passing the test. And how I'm getting this information, how do I know this is the second hardest section? Well, I'm getting my information from hamstudy.org. I have a long list of metrics, over 1,000 different tests that have been ran, actual tests with people taking their license exam, and TC9 is the hardest section. So here we go, T9A01, which is, what is a beam antenna? We're going to talk about that, but I'm going to cover the answers only, and I'm going to give you background on the answers to keep this as condensed and focused as possible. I hope that helps. C, at least that's the answer that is on the question pool, and an antenna that concentrates signals in one direction. So if you're thinking about a vertical antenna, something on like a handheld, this is omnidirectional. It fires off RF in all directions. Well, with a beam antenna, a Yagi antenna as it's often sometimes called, there are other types of beams too. There are elements behind and usually in front of the actual driven elements that are connected to your radio that focuses the RF in one particular direction. And they use the word beam as though it's like a flashlight beam. It's a little bit wider than that, although you can add more elements and that will tighten the pattern. T9A02, which of the following describes a type of antenna loading? And that is A, inserting an inductor in the radiating portion of the antenna to make it electrically longer. What they're basically saying is adding a coil, likely to the bottom of an antenna. Well, that coil has a length of metal, right? So if you're adding a coil that has been, at one point was long and then coiled up, you're adding an electrical length to that antenna, and that would be loading the antenna. T9A03, which of the following describes a simple dipole oriented parallel to the Earth's surface? And that would be B, a horizontally polarized dipole. If you think about the Earth isn't flat, but you know what I'm saying. The flat land that you're standing on, if your antenna wires are running parallel to the flat land, you can consider that horizontal. Again, flipping it around, if you had an HT, some kind of vertical antenna, that would be vertically polarized. T9A04, what is a disadvantage of the rubber duck antenna supplied with most handheld radio transceivers when compared to a full-sized quarter wave antenna? And it's a simple answer. A, it does not transmit or receive as effectively. And let's do a comparison. Here is the vertical antenna that came with this HT. That is not 1/4 wavelength of 2 meters, and that's a pretty simple calculation you can do and be relatively close. If you took 2 meters and took 1/4 of 2 meters, that is not going to be that length. What's a little bit closer is something like this. This is a signal stick glow-in-the-dark antenna. This is closer to 1/4 wavelength on 2 meters. This is going to perform better as a receiver and a transmitter. By the way, nice little segue here, hamstudy.org is funded by and basically allowed to work as it does because of people buying signal stick antennas. The owner of hamstudy.org does this for free and produces these. These are handmade in Utah. The sales of this antenna go directly to fund the servers and the web space that runs hamstudy.org, as well as the testing software that many of you have used in the last year for getting your test online. So if you're interested, the link will be in the description. You can get yourself a signal stick antenna. I highly recommend it. They're the antennas I use on my HTs. T9A05, how would you change a dipole antenna to make it resonant on a higher frequency? Well, the answer here should be simple too. C, shorten it. So if this is a 2 meter antenna, right? If we wanted this to be resonant on, say, 146.520 megahertz. But we also wanted to have, say, a 20-meter dipole, which is going to be resonant on 14, call it 14.250 megahertz. Well, that's a really long antenna. That's going to be like over 14 feet for quarter wave. Well, if we wanted to get it down to 2 meters, not saying you do this, you just shorten the lengths up, right, until it's 1/4 wavelength of the frequency that you want to operate on. Once you kind of get the idea, quarter waves, a dipole is 2 quarter wave pieces that make up a half wave antenna. Once you start getting into the mindset of half wave, quarter wave of the frequency you're on, then this makes a little bit more sense. So if you want to increase frequency, go higher up the frequency space, you shorten that antenna. If you want to go down, lengthen it. T9A06, what type of antenna are the quad, Yagi, and dish? Two of those you've probably heard of. A quad, though, well, what is that? Those are basically a directional loop antenna, or a series of loops that are put together to make a directional antenna. I kind of already explained Yagi, and you probably are familiar with a dish antenna. These are directional antennas, which is option C, meaning, again, functions a little bit like a beam. They're going to put RF more in one direction and less in other directions. So that's a beam antenna. TA907, what is the disadvantage of using a handheld VHF transceiver with the integral antenna inside a vehicle? A, signals might not propagate well due to the shielding effect of the vehicle. You're literally in a box of metal, and although, yes, there are windows, the RF signals aren't going to be able to get out of those windows as effectively if you had just mounted an antenna on the roof. I have a couple of videos on mobile antennas and mobile radio setups. I'll link them in the description so you can check it out. But generally, if you want to get serious about a mobile antenna, it's best to have the antenna outside the car. T9A08, what is the approximate length in inches of a quarter wave vertical antenna for 146 megahertz? So there's a little bit of remembering you're going to have to do here. 146 megahertz is a part of the 2-meter band within amateur radio space. So the answer for this is C, 19 inches. And if you were to take 19 inches and multiply it by 4, again, because it's a quarter wave antenna that it called for, you'd get roughly 76 inches, which relatively is about 2 meters. That would be a full wave antenna. Quarter wave, full wave. Hope you're getting the idea. There's a bit of a theme going on. T9A06, what is the approximate length in inches of a half wavelength 6-meter dipole antenna? You're going to have to know the frequency spaces that 6 meters is generally in, which is about the 50 megahertz space. The answer for this is C, 112 inches. So there's a calculation you can do for this, and there's a couple of calculators online. I just base things off of quarter wavelengths. So if you took 234 and divided it by the frequency that you wanted to find the quarter wavelength on, say 6 meters, which is about 50 megahertz. So if you took 234 and divided it by 50 megahertz, let's call it, which is just close to 6 meters, you'd get something like 4.7, which is going to be in feet. You multiply that by 12, and that will get you about 56 inches. Now, if you took that number and doubled it, that would get you to 112. So that's about, kind of backing yourself into the answer. There are a multitude of calculators online if you're so inclined to. Pick yourself up an ARRL handbook if you want to know a lot of the background information on why we use these numbers, and some other important calculations if you are interested in building antennas. T9A010, in which direction does a half-wave dipole antenna radiate the strongest signal? So in an ideal configuration, a dipole is going to look just like a horizontal line, and it's fed in the middle. So your coax is going to be right here, trailing down. The way that this radiates is kind of like a donut of RF that goes all the way around it. So it radiates the best from the broad side of the antenna, and that's the answer to this question, C, the broad side. The tips, the ends, are actually nulls with very little to no RF coming out of those areas, and most of it going out this way and this way. So if you had a firm fixed dipole, you could actually rotate it and get a tad bit of directionality out of it. T9A11, what is the gain of an antenna? The answer is C, the increase in signal strength in a specified direction compared to a reference antenna. Oftentimes the reference antenna will be the dipole. And if I had a beam where I've stacked elements in front of this radiating element, I'm going to get gain in the direction that I put those elements in wherever I point it. Again, going back to this beam concept. Well, that increased power or increased signal strength that's coming off of that forward part of the beam, that is going to be compared against that of a regular dipole, and that difference is your gain. T9A12, what is an advantage of using a properly mounted 5/8 wavelength antenna for VHF or UHF mobile service? The answer to this is A, it has a lower radiation angle and more gain than a quarter wavelength antenna. Hamstudy.org does a really good job of this. They add bold words to the key points of the answer and part of the question, and then there's an information tab you can click on that will give you more information. But what this comes down to is if this were a 5/8 antenna, it's going to have a lower takeoff angle or lower radiation than, say, a 1/4 wavelength antenna. A 1/4 wavelength antenna is going to have high angles that the RF is coming off of, which is going to work good for a repeater, but may not work well if you wanted to work primarily simplex and you had your antenna high enough that you could get some work done there. So 5/8 is generally going to be the way to go in certain situations, quarter wave in other situations. It's going to depend on your area also. A lot of repeaters around me, they're very, very high up on mountains, so I tend to go with quarter waves. It's just my preference. All right, so we've moved from the sub-element 9A, now we're going into 9B, which is going to get a little bit more into the weeds and talking about some of these interesting parts of antennas, like B01. Why is it important to have a low SWR, and I'll just give you the acronym here, standing wave ratio, when using coax feedline? And the answer is B, to reduce signal loss. That is a very compact way to talk about something that's fairly complicated. And again, if you are using hamstudy.org, you're playing along at home, click that information tab. Basically what's happening is if you have a high standing wave ratio, that means that your antenna is mismatched from your radio. The resistance in the feed line and at the antenna that's presenting itself to your radio is not the 50 ohms that the radio expects. When you get right down to it, an antenna is a circuit. It's a part of the circuit of your radio. And if you've got something of a mismatch of that 50 ohms, the difference that you're putting out in power is getting wasted in heat and other things. You get signal loss, signal degradation from that. So the closer you are to the standing wave ratio, the more signal is being applied to your antenna and the more is actually radiating out of the antenna. And T9B02 comes right back with something to reinforce that. What is the impedance of most coax cables used in amateur radio installations? The answer is B, 50 ohms. That's the standard. TVs use 75 ohm feed line. You know, you don't want to use that stuff unless there's a very specific case, which there are. But in almost all situations for amateur radio, particularly if you're in the VHF UH space, stick to 50 ohms. T9B03, why is coax cable the most common feed line selected for amateur radio systems? The answer is A, it is easy to use and requires few special installation considerations. Coax is, for just a simplistic way of looking at it, you have an insulator, usually black, some kind of rubber coating, around a metal shield that fully encases the metal center pin, which is right here, which is separated from the shield via a dielectric, a non-conductive substance. That is the two parts of the antenna, your negative side and your positive side, or whatever you'd like to call it. This is very easy to run out of a window, out of a vent, out of wherever, along the ground, by metal, all kinds of things, and not have a problem with connecting to your radio or your antenna. What happens with other feed line types, because that's assuming what I think you're thinking, there's other feed line types called ladder line, which are two equally spaced wires that make up the positive and negative side of the antenna, basically. Those are extremely susceptible to being close to metal, walls that have, lath or stucco with the chicken wire behind it. It doesn't want to be too close to anything metal. And so that actually makes it really difficult to bring into a home that you'd run as a ham shack. So that's why we use coax. It's generally very easy for what we want to do. Now, for all you ladder line lovers, I'm not taking anything away from ladder line. It's just a more specific use case where you deploy it. TB904, what is the major function of an antenna tuner? And then in parentheses, they put antenna coupler. Important note, because tuner, it gets confusing. The answer is A, it matches the antenna system's impedance to the transceiver's output impedance. We already talked about the 50 ohms impedance that's expected at your radio. Well, what happens, like that first question, if the SWR is not 50 ohms, or the match to the radio is not 50 ohms, and you get that high standing wave ratio as a result or a symptom of a mismatched antenna? Well, you may put an antenna tuner, or in this case, a much better word, an antenna coupler in the loop that will adjust the feed point impedance to be 50 ohms for the transceiver. Now keep in mind, there's so many discussions on this point, and I'll keep this very light. An antenna coupler, antenna tuner, isn't making the antenna any different. If this is still cut wrong, it's still the wrong length. So if I took an antenna tuner and I tried to tune this up on 20 meters, it may do it, but I'm not going to be getting the best reception and the best signal in and out of this antenna. So it's making the radio happy, it's satisfying its needs, and the radio is going to try and put all that power through your tuner, coupler, and into the antenna. But it doesn't it doesn't hide the crimes, if you will, that we might have done with the antenna we're using. Now keep in mind, some antennas are designed to not be within 50 ohms. It's designed to be outside of that space. And that's, again, okay. You just have to know exactly what you're doing when you are attempting to use a tuner or a coupler in this case. There's nothing really wrong with using a tuner or a coupler, unless it's to, again, hide the crimes. Like I built an antenna for 40 meters, and I'm just going to tune it down to 20. You might be not very satisfied with the results you get if you use the coupler to get it into that space where the radio will transmit at full power. TB905, in general, what happens is the frequency of signal passing through the coax cable is increased. And D, the losses increase. TB906, which of the following connectors is most suitable for frequencies above 400 megahertz? Type N connector, option B. Most radios, particularly if you're on the high frequency side of amateur radio, the bigger antennas, the really long distance beyond line of sight communication, what you get more of when you get your general license, we're going to use these PL259 connectors. It's got a collar on the outside and a big center pin. Type N connectors have also an outer collar, also a center pin, but then there's an inner kind of collar as well, and that prevents RF losses through the connector. As you start to get higher in frequencies, 400 megahertz is the reason why they use that number, is because as you go from 400 megahertz and up, PL259 will incur losses at the connector. So that's why we use something that reduces those losses, like a Type N connector. T9B07, which of the following is true of PL259 coax connections? C, they are commonly used at HF frequencies. Yeah, because again, they're less problematic with loss. So hopefully we're building a narrative, I hope, as we're answering these questions, and you start to get the idea of why we may use one thing over another thing. TB908, why should coax connectors exposed to the weather be sealed against water intrusion? Water's a key word here. A, to prevent an increase in feed line loss. Coax has a dielectric in the middle, and there's a divider between the shield and the center pin, and if you've got a connector, these connectors are not waterproof. They were not designed to be waterproof. Eventually, over time, you can get water ingress if you don't weatherproof your coax. Once the water gets in coax, it's difficult to get it out. So far so to the point where you actually have to take it off the antenna, hang it up, and then leave it for an indiscriminate amount of time until that water evaporates, goes away, gets reabsorbed by the atmosphere, the humidity levels change and whatnot. So the best thing you can do is use something like coaxial. Self-amalgamating tape is what we often call it. Most ham radio stores sell this, and you can buy this online as well. It's a tape that doesn't stick to other things but itself. So as you're wrapping, you're tightening the coax, you're going in the direction of the turn of the PL259, you're going to wrap it tightly, and you're going to want to seal from the threads to the collar that goes over the top of those threads. And you want to wrap it real good. About 6 inches will get you a PL259, and it's got a lot of stretch to it, so give it some stretch, pull, and wrap, overlapping about half of the tape as you go is what I generally do. And if you want an extra level of protection, take some decent 3M electrical tape and then wrap that whole thing up too. It'll give you a little bit of protection to UV sunlight. T9B09, what can cause erratic changes in SWR readings? B, a loose connection in an antenna or feed line. That is one of the things. There are many things that could do this, but that is a very simple thing you should always check. Check the back of the radio. Is that, you hear this? Do you hear this kind of thing as you're tightening it? That might be your problem. Make sure all your connections are tight, particularly for you guys that operate from the field. You go outdoors, you set up an antenna, you connect. Always check that before going live, or if you notice a problem, start with the simple stuff and work your way up. T9B10. What is the electrical difference between RG58 and RG8 coaxial cable? C is the answer. RG8 cable has less loss at a given frequency. Coax is built all kinds of different. Some are more flexible, like this one, and it's got a thin diameter. This makes it great for portable work, whereas what I use at home is called LMR 400. It's very thick gauge stuff. And here's actually a jumper cable of it. Can you see the difference? It's quite staggering. LMR 400 will drastically reduce the losses over RG58 and RG8. It's also kind of hard. You can get flexible variants of LMR 400, but just keep that in mind as well. These are all important things to consider. This is probably not the right coax to take portable because it's also heavy too. D9B11 is showing off a little bit. It's a stuntin, it's ham radio stuntin. Which of the following types of feedline has the lowest loss at VHF, UHF? And that's a C, air insulated hard line. That's literally a hard, instead of a shield that is made of woven metal that is flexible, hard line's flexible to a degree, but not this way, if that makes sense. It's actually a rigid structure that can bend, not appreciably bend, that has a floating center pin, usually isolated by some plastic standoffs to kind of hold it in the middle. That is the best loss-resistant coax you can get. Generally very expensive though, so keep that in mind. Well, hey, that's sub-element T9, the second hardest sub-element within the tech license. I hope this was helpful. I hope this gave a little bit of background. I think cutting out to just the right answers is allowing me to spend more time explaining why the answers are right. So I'd really love it if you told me this is helpful or not helpful. What am I doing wrong? I'll try and correct it as we work through the rest of these sub-elements, because I have a lot of fun doing these to kind of put more context in it. A lot of people say that if you want to effectively get your test quickly, you kind of just have to remember the answers, which I think is true, but I think doing it this way allows me to kind of put some more context behind it, and I hope that helps. I really do appreciate your feedback. If this is enjoyable, this was helpful to you, if you got value out of this, click the thumbs up, consider subscribing. I do, as well as all my other videos, my short form videos, I live stream every Saturday at 5 p.m. Pacific Standard Time. And I'm also hosting Ham Nation, which is every other Wednesday at 6 p.m. And those are Pacific times. Okay, I'll talk to you later. Thank you so much for watching. See ya.